Right. Bismillahirrahmanirrahim. Okay, everyone, can you all please look at question 20 of your exercise 14.2. Okay, right. So PQ and R are structural isomers with the molecular formula C4H8. Okay, so that's a valuable information for us. All three compounds readily decolorize bromine in the dark. So decolorization of bromine is important, essential for the identification of alkenes. Okay, how do we know that they are not alkanes? Because alkanes wouldn't react with bromine in the dark. That's right. P and Q do not exhibit stereoisomerism, but R exist as a pair of geometrical cis-trans isomers. Okay, so sorry. What does it mean that R exists as a geometrical isomer? So there are two requirements for a cis-trans isomerism. The first requirement is the double bond, the presence of the double bond. The second requirement is that each atom or group of atoms bonded to the C double bond C must be different. Okay, so I would just say that they are group A and group B. Whatever it is at the moment, I wouldn't know. Okay, likewise for the other carbon in the C double bond C, it must also be attached to two different groups, C and D. But whether A and C are the same or different, that's fine. Okay, but most importantly, A cannot be the same as B, C cannot be the same as D in order for R to have a cis-trans isomer. Okay, right. What else? All three compounds react with hot concentrated. So for those of you who just joined, Amelia, we are on question 20. Okay. Apa tu? Amelia, okay. All three compounds react with hot concentrated acidified potassium manganate. So this means that it is a strong oxidation of alkenes. So you should all be referring to your notes under strong oxidation to produce a variety of products shown in the table. Okay, so these are the products of strong oxidations of the double bonds in P, Q, and R, as we all know that they contain double bonds or they contain alkenes as a functional group. S reacts with 2,4-DNPH. So S is that the product of the strong oxidation of compound P to form an orange crystalline, but does not react with Fehling's reagent. So that means this statement, okay, something that you have not covered yet, this statement indicates that S is a ketone. Okay, and the structure, the functional group of a ketone is a C double bond O attached to two carbons. Okay, right. So those are the hints given to us, and now we have to work out the structural formula. So when you hand in your work later on, make sure that you leave your final answers in the correct structural formula. Okay, so yesterday I saw that most of you forgot to convert it to structural formula because you just copy what I did, which most of the time I will be drawing this plate formula. Okay, but you must always go back to the question and read for any specific instructions on what to leave your answer as. Okay, right. So compound P. So if you look at the question, compound P says that, compound P contains a C double bond C attached to things that we don't know. Okay, but we know that when we treat P under strong oxidation, we produce two products, CO2 on one side and S on the other side. Okay, now if I look at the formula of S, C5h10, and that S is a ketone, C3, 1, 2, 3. Okay, hydrogen, 1, 2, 3, 4, 5, 6, and 1 oxygen. So that means this is already the structure of my S. Okay, right. So the way that I'm going to draw this is that I'm going to turn my product sideways so you can see it clearly. Okay, because that C double bond O, the double bond, came from the original C double bond C. So please refer back to your notes. What must be attached to each carbon in the double bond in order to get these products? Okay, so I'll leave it at that, and I want you to work it out yourself. Next is Q. Q is also an alkene attached to 4 things that I don't know at the moment. But what I do know is that when Q undergoes strong oxidation, I get 2 products, which is CO2. That's one of the product. And the other product is CH3CH2COOH. I hope you can spot from the structural formula that it is a carboxylic acid. Moving on. So when I draw out the product, again, I will draw it sideways, hoping that you can spot it quickly. COOH, I always start with my functional group first, followed by CH2, CH3. So your task is to work in reverse. Okay, what must be attached to these bonds in order to give you the particular product, right? That's P and Q. R, same thing. R also compounds double bond. Anything else you need to know about R? Is the fact that it is attached to, each carbon is attached to 2 different groups, but again, that doesn't help us much with identifying the structure. But later on, when we do get the structure, we can always check, are the carbon in the double bonds attached to 2 different things? Okay. Right, for now, we're just going to use the strong oxidation products. Again, R undergoes strong oxidation. Somehow, this time, it only produces 1 product. Whereas when you treat an alkene under strong oxidation, you should get 2 products. 1 product comes from half one side of the double bond, and the other product comes from the other side of the double bond. So what does this imply? This implies that both sides give the same product. Okay, so that means if you look at the product, it's CH3COOH. Again, that is a carboxylic acid. Okay, so the left side gives C double bond OH with a CH3. Okay, and the other side is also giving you the same product, which is your ethanoic acid. Okay, because they are the same type, so we say that it produces the same product under strong oxidation. Okay, it doesn't mean that they don't break, the double bonds don't break completely. Okay, it doesn't mean that there's only one molecule. Okay, there are two molecules, but they are of the same type. So you will again use the same method. You will work out based on the product what must be attached to this bond and what must be attached to that bond to give you COOH here and then CH3 here, right? Other than that, I think that should be enough to help you to identify the structure of PQR and S. The structure of S is already here. It's just that you need to leave it in the correct structural formula. Okay, so I will let you copy this down if you haven't, and please let me know if you are done copying. Then we will move on to the next question. Any problems? Please let me know, okay? Done or still copying? Please let me know. Wow, now give thumbs up sudah, ha? Hello, what about the others? Wow, I have 4 thumbs up. Ashraf, Hannah, Hazwan. Okay, so I'm guessing you guys are done. Mr. Fabian, Ria, Kaushan. Okay, thank you, everyone. Right, so please do that. Don't hand in your answer as it is, like literally what you copied from my slides. Please give me your answer and the answer to the question. As usual, just upload it to the OneDrive folder. Okay, next question is question 22. Okay, so this is a reaction of a cyclohexene with HCl to give you a chlorocyclohexane. So cyclohexene is the cyclic alkenes, right? And the representation that you are given is in skeletal formula. Okay. Maybe it's not something that you are familiar with already, the skeletal formula. So I'm just going to tell you that there are some things that are not shown in the skeletal formula. There is a hydrogen here, and there is also a hydrogen here, because if you notice that each corner is a carbon, so this carbon has 3 bonds that are shown, and the 4th bond is the carbon-hydrogen bond that is present, but just not shown, okay? Likewise, for this carbon, also got 3 bonds that are shown, and the 4th bond is not shown, but that doesn't mean that it's not there. Okay, other things attached here are not so important. They are just carbon-hydrogen bonds, 2 carbon-hydrogen bonds. In a skeletal formula, these bonds are not shown. Why do I say that they are not important? Because they are not the functional group that we are interested in. We are interested in the double bonds, and we want to draw the mechanism. Okay, when they ask you to suggest or draw the mechanism, that means you have to draw the arrows, draw the charges, draw any dipoles. Okay, so here you have whole or partial charges. Whole charges means positive, negative. Partial charges means delta plus, delta minus. Represent the movements of electron pairs by curly arrows. So you need to show every single thing. I don't know if you still remember, this mechanism is called the electrophilic addition mechanism. Okay, so let's start. I am going to keep the skeletal formula as it is, except on the functional group. Okay, so that you know that there is a hydrogen there, right? And then my other molecule is a HCl. Okay, so we are, as we go along with the questions, we're also revising because your L6 prelims is on. Okay, so I will update you the date later on once it's confirmed, but there will be an prelims for you online. Okay, back to this. HCl is a polar molecule. That means they have dipoles, and as we all know that hydrogen is delta plus and chlorine is delta minus due to the difference in electronegativity. In this case, your double bond is the nucleophile and your slightly positive hydrogen is the electrophile. So what happens is that nucleophiles will donate its pair of electrons to the slightly positive hydrogen. That means they form a new carbon hydrogen bond, in which case your hydrogen chlorine bond needs to be broken. Otherwise, hydrogen would have two bonds, and hydrogen can only form one bond maximum. So the next step is to break the hydrogen chlorine bonds, and because chlorine is more electronegative, that means chlorine will get the electrons. Okay, so this is where you form an intermediate. Now the question is, you notice that my arrow is coming from the double bond. The question is, where do you form the carbon-hydrogen bond? Is it here or here? Okay, there are two options because there are two carbons on the double bond. So if you look at the product, your chlorine goes to the carbon on top. Actually, for this question, it doesn't matter because wherever you put the chlorine will be the same anyway. Okay, but for this purpose, I will just tell you that the chlorine is on the top carbon. So that means your hydrogen must have gone at the bottom carbon. Okay, so your intermediate, what we call the carbocation intermediate. So that's your original carbon-hydrogen bond. Your newly formed carbon-hydrogen is the one in blue. Okay, and then what happens when the lone pair of electrons is donated? Okay, one of the double bonds will be broken, so you're left with only a single carbon-carbon bond. And you notice that this carbon only has 3 bonds, so it has a positive charge. That's why it's called a carbocation. Okay. And then what happens to your chlorine? Because chlorine gets the electrons, it now develops a full negative charge. So students can easily make the mistake of writing the charge as delta minus because initially it was delta minus. Okay, after it has obtained the electron pairs from the bond, it develops a full charge, full negative charge. So you no longer have the delta. Okay, next, you've got a positive charge here on the carbon, and you've got a negative charge on the chlorine. And you know that chlorine has a lone pair of electrons that it can donate. Okay, so then you get this. So I'm just going to draw the original hydrogen that is in orange, and then the hydrogen that came from HCl will be in blue. Okay, and that's your chlorine attached to the top carbon. Okay, now in skeletal formula, we don't have to show the hydrogen bonds. So if I omit the carbon-hydrogen bonds, I'm left with this molecule with the carbon-chlorine bond shown, which is exactly what your product is, okay? Don't think that, oh, only chlorine is added, my hydrogen is not added, okay? So always follow the mechanisms and revisit your skeletal formula, okay? The proper or the correct way of a skeletal formula is where all your carbon-hydrogen bonds are not shown and only the functional group. So this is a skeletal formula of chlorocyclohexane. Okay. Okay, so I'll let you copy that down. This one you don't have to hand it in because I'm already giving you the answer anyway. Please let me know when you're done, okay? Okay, I see a few thumbs up already. Thank you. What else have I not done with you guys? Okay. Question 17, because I did question 17 with the other block. So that will be the last question of the day. So let's have a look at question 17. Okay. The formula of a compound. Okay, so the only important thing that I want you to get out of here is the C5H10, which may be branch, straight, or cyclic. Draw a displayed formula of C5H10 as a branch chain hydrocarbon. Okay, so C5H10, that looks like it's a general formula for an alkene.
Okay.
Yes, correct. Okay, right. So there are a few accepted answers. There are three, actually, three isomers of C5H10. Okay, so I can tell you that it contains a double bond. Okay, it can be branch. It can be straight chain. Okay. Okay. Oh, sorry. It cannot be a straight chain. It has to be branched. Cannot be straight chain. So that means something like this or somewhere lah. Don't forget the double bond also, okay? That's just a hint, right? And read the question. They want displayed formula, so make sure you leave your answer in displayed formula. Okay, next. I just give you the hint quickly. Yeah? Pentuene is a carbon, 5 carbon, pentene. 1, 2, 3, 4, 5. And the double bond is at position number 2 and 3. Okay, so you are required to draw the cis trans draw and label the structural formula of the cis trans. Okay, so this one, I want you to show your cis trans like this. Okay, and structural formula, you write it as CH2CH3, not C2H5. Okay, please avoid writing that down. For example, okay, but I want to see your frame to be up and down, clearly shown. Bonds going up, bonds going down. So I'll leave you to do that as well, because that is quite straightforward. So please just copy down my hints. In the spaces below, draw the structural formula of two alcohols, which would each, okay, so we have 40 minutes left, which would each produce pentoene on dehydration. So we are now working in reverse. Okay, we get one product, same product. Okay, two alcohols that would give pentoene. 1, 2, 3, 4, 5. Okay, so 2 and 3. Now this reaction is called the dehydration of alcohol. We have actually covered this under the production of alkenes in your notes. Okay, now if we were to work in reverse, it means we are looking at the hydration of alkenes. Okay, forward is called dehydration of alcohols, and going in reverse would mean hydration of alkenes. Okay, so what happens is that between your second and third carbon is where you are going to add your water. But water is added in such a way that one carbon will get hydrogen, the adjacent carbon will get the OH. Okay, what about the other structure? The other structure is if carbon number 3 gets hydrogen, carbon 2 gets OH. Okay, so you may ask, why are we only looking at carbon 2 and 3? Because that's where your double bonds are. So if we now look in the forward direction, removing OH from carbon 3 and H from carbon 2 will result in the formation of a double bond between carbon 2 and 3. Okay. Likewise, for the second structure, removing OH from carbon 2 and removing hydrogen from carbon 3, that means your carbon, if I erase this, your carbon now have 3 bonds. So I purposely leave out the hydrogen. Okay, your carbon have 3 bonds. So in order to make this carbon happy, you need another bond across the C, single bond C, to become a double bond. Okay, so that means the two alcohols that can give you to the same product of alkene, which is pentoene, is 1, 2, 3, 4, 5, pentantriol and pentantool. The question wants you to answer in structural formula. So please make sure you leave that, you write the structural formula for these two molecules. Okay. Let's see, what's the next? One of these alcohols exhibits optical isomerism. Draw the structural formula of the two isomers of this alcohol. Your structures should clearly indicate the three-dimensional nature of the structures. Okay, so one of these alcohols will have an optical isomerism. Optical isomerism is the requirement is that the molecule has a chiral center. So one of these has a chiral center. Won't tell you which one, you will decide, okay? So after you have decided which one between these two have a chiral center, you are to draw the optical isomers, okay? When drawing the optical isomers, I want you to start with, as usual, the structure, the tetrahedral structure, okay? Sorry, wrong. So you just copy everything. Now, I noticed that when I was marking your paper yesterday, I still get, no, not your paper. I still see some students getting confused with this reflection. Now, if you put OH on this solid bond, the reflection of that molecule will also have OH on the same solid bond. Okay, I can assure you that they are two different molecules. So you just follow the reflection on the bond. Okay, whoever is sitting on the dotted bond will also be sitting on the dotted bond on the opposite side. So I don't want to draw too much, otherwise I will be giving away the answers. Okay, last one, because F you don't have to do, because F will be under polymerization, which will be covered later on. Okay, 4 minutes left. Pen2-in decolorizes aqueous bromine. Suggest the structural formula of an isomer which does not decolorize aqueous bromine. Okay, now there's a problem with this question because it should have been does not decolorize aqueous bromine in the dark. Okay, because that's what it means. They want you to draw an alkane that has a formula C5H10. Remember, C5H10 can be branched, straight, or cyclic. Okay, so it can be straight, branch, or cyclic. So you have to find a structure that will give you an alkane. Yes, I know it's an alkane with a formula C5H10. So it must not contain double bond. Okay, so this question, I feel like it's not complete when they say C5H10 does not decolorize aqueous bromine. We all know that alkanes can decolorize bromine in the presence of sunlight or in the presence of UV light. So they should have elaborated that question by saying that this C5H10 for this particular question does not decolorize bromine in the dark. So then it will be clear to you that the C5H10 must be an alkane containing single bonds, and there is no double bond. Okay, so there is one structure either from the straight, branch, or the cyclic chain that will give you the formula C5H10. Okay, all right. Any questions before we go or before we get disconnected? We have about less than 2 minutes left. Ashraf, good. Abby, hearts back at you. Okay, everyone okay? No question?